From ContainerDays Hamburg, this video is proudly presented by jackc.
How many of you have heard of Transactional Outbox Pattern? Please raise your hand. Okay. How many use in production? Okay, not so many. Okay, let's revisit or learn something new about Transactional Outbox Pattern, also in Go. So I'm Nikolay, a senior software engineer in Zalando, working in Helsinki office in Finland. And I also offer of pgx-outbox library, which is a simple library to implement transactional outbox pattern in Go. And this is my journey, how I ended up using Go language. And I started with C, Java, and Kotlin. So yeah, I got this the title and the talk inspiration from this great article by Gunnar Morling, who is now working, I think, in Confluent for Kafka, but before that, and now he writes a lot of articles about transactional outbox pattern and CDC, change data capture, and I really enjoy them. And also I added some of my personal experience into this talk. So let's start with the problem. What's the problem? And the problem is called do-or-write problem. So we have, once we started to build microservices, like 8 years ago, something, we started to get this kind of problem. Before, with Monolith, it was, this problem kind of didn't exist. So imagine like there is a service A, which has to do 2 writes, one of them to database and one for to message broker. Imagine you place an order in e-commerce, and then service A has to store that order into database, insert to database table, and then send message to, for example, to Kafka or another RabbitMQ broker, and that would deliver message to service B, and service B would eventually send customer confirmation email or SMS. And sometimes that's even a legal requirement. And if the order is placed, we have to send customer confirmation. So if that doesn't happen, then the legal requirement is violated. And the problem is if we have this kind of requirement that the write has happened to 2 systems in a kind of atomic way, or it doesn't happen at all. And if only one write happens, then that's the problem, and system become an inconsistent state. So that's the do-write problem, and how we can solve that in general and in Go in special. So I will present you 3 naive approaches, and none of them actually work at first. Let's start with the first one. So first we write to the database. So we place our order to database, and then after transaction is done, we send message to message broker. But the problem here that the message broker might be not available. Maybe it ran out of disk space, maybe networking issues. So we cannot send the message to the message broker, but the order is already stored to the database. Also, another potential failure scenario that our service port would crash after the database transaction happened, but the message wasn't sent. So we end up in inconsistent state of our system, and customer never get confirmation of an order, and legal requirement is violated. So if we reverse the order, we first try to send message to the message broker, and after that it's successful, then we store to our database, the order to database. So the potential problem that database transaction can fail, it would be rollback, but the message was already sent to message broker, and it's difficult to roll back that message into the message broker. And also service A port might also crash after the message was sent to the message broker, but it was not stored to the database. We again end up in inconsistent state and legal requirement violations. So this is a third approach. This is kind of anti-pattern, and it caused several incidents in production, not in our team, but I heard. So So we start transaction to the database and we insert the order, but instead of commit, we go and check if we can send message to the message broker. And if that one succeeds, then we would commit transaction. But if that one sending message to the message broker failed, then we would roll back transaction. So in theory, it works fine, but in reality, there is a big issue about that, because if we keep transaction open and message broker start misbehave, it takes a long time to reply. Then we keep the connection open in the connection pool, and connection pool might get exhausted. So all other orders which we have to store in the database, they would be rejected very early. And even though we send the message to the message broker, then database commit might still fail, even though we already did insert. So there is a solution to that problem, and it's called Transactional Outbox Pattern. It's one of solutions to the right problem. So how it works? So when we write data to the database, we open transaction and we store our intended domain entity order in our case. And in the same transaction, we store the message which we intend to send to the message broker. And then we commit transaction. So in that way, it happens atomically. Either transaction is committed or it's not committed at all. But then we have to introduce Outbox relay, which is a different entity which is going to poll our Outbox table. Outbox table is a new table which we introduced for Outbox messages. It would read messages from that and eventually send them to the message broker and acknowledge them or delete them in our database Outbox messages table, which we have just introduced. So that actually works. Of course, there are some pros and cons about that. We discuss later. This is how this is example of the table. Like the very simple. Basically, you need to store payload anyway. Most probably JSON. You need some ID, so you can reference those messages. Then you acknowledge or delete them, and then depending on your use case, you can add additional metadata to this table. Yes, so Outbox pattern, it solves the do-right problem. It has definitely advantages. It provides us atomicity. So now we have at least once delivery to the message broker, and now so that happens kind of in atomic way. We store the order and the message in the table, or do not store them at all. So there is no we stored one of them and didn't store the second one. But of course, it comes also with some disadvantages. So first of all, we introduced message publication delay, because now we don't immediately send the message to the message broker, but first we store that to the database, and eventually that Outbox relay would get those messages, grab them, and send to the message broker. So we also need some additional code, or also even deployment unit to maintain Outbox relay. Also, our consumers might need to deduplicate the messages because now we get at least once delivery guarantee, not just single delivery guarantee. And also we increase the load on the database resources. So now we have to decide. So we can store the messages in the same transaction, but we need to weigh how we get those messages out of the table, out of the SQL, and send them to Kafka. So in here I show you an example of the table. It has some payload, which is not very visible, some ID. And then we have several options with SQL databases how we can get those messages to be published by Outbox relay. One of the options is periodic polling. It's very naive. We just use select. We do that periodically, get the data. This is simple, but not very efficient. And the second option is called log-based change data capture, or CDC. So let's start with the simple approach first and discuss that. So we can do periodic polling. We select, And then we need to wait, after the publication, we need to wait a way to mark those messages as published. We can either delete them, maybe we can introduce additional field when we publish them and update that field. There is a more sophisticated, more efficient approach. We store kind of the latest ID in a separate table per consumer of the message. So there, if you want to implement that in Go, there are multiple libraries which support this kind of transactional outbox pattern. There is Watermill library, and there is the child library called Watermill SQL. So that can do exactly that. It can select the messages and then acknowledge them and send to configure data sync like Kafka. So there is pgx-outbox library, which I maintain right now. There are some even more libraries, and in general, you can take any SQL general purpose queue and adjust that to implement transactional outbox pattern for your purpose. So I would like shortly to introduce my library, which is called pgx-outbox. pgx is the most popular driver for Postgres and written in Go, and that library has strong focus on Go. So it provides out of the box, implements the messenger and some building blocks like a writer, forwarder, that helps you to build transaction outbox pattern. It uses, for simplicity, it uses this update approach to mark published messages. And this is how it looks like. So you saw this architecture of transaction outbox pattern, and this is PG outbox architecture. So in the order service, there is outbox writer, which helps you to actually join the existing transaction, and if you store the order, it can help you to store the message in the same transaction. So it helps you to transform the message, join the same transaction, and store that to the Postgres. And then it comes also with Outbox Forwarder, which under the hood it helps you to implement Outbox Relay, which can be a separate cron job or like single pod deployment. There is reader and publisher, and the reader would help to read the messages in the same format which they were written by the writer, and the publisher would send them to SNS or Kafka. It's extendable, like you can change implementation. And right now, out of the box, it supports SNS, but can be changed to Kafka and something else. And then reader also acknowledge the messages by updating the field in the database. This is how Outbox Writer interface looks like. So there is a parameter for transaction, because it's transaction outbox pattern. It has to join existing transactions, so it's one of the parameter. Like the first method support 2 types of transactions from the standard library and from PGX API. And the second method allows you to send multiple messages for the same entity if you need, and you can do it efficiently using send batch and prepare methods. So this is how it can look like in tracing. A PGX driver, if you use the pool, you can add very easily. You can add tracing exporter there, and this is how it looks like. We start the transaction, like query begin, then we insert to the orders, we insert to the outbox messages, and then we commit transaction. So we get both at the same time, orders and outbox messages. And now we need to read those messages from the outbox table, and the polling approach is viable, but it's better to use that for low traffic because there is like always trade-off between how often you pull and the delay which you introduce, and also if you have a high traffic on the Postgres database or SQL database, and you're polling too often for the outbox messages, then your kind of useful business workloads, they might suffer because of that. Also, update and delete operations in Postgres, they create dead tuples. Basically, it makes a copy of the row. If you update even a single field, it creates the copy of the whole row, and then later they have to be garbage collected. So to solve the problems of polling approach, there is another approach. It's called log-based CDC, and log stands for write-ahead log in Postgres. In MySQL, it's called binlog. So if we use that approach to read the outbox messages, then we get much lower publication delay. We also reduce database load because we avoid select polling, and we avoid creation of dead tuples. And then another benefit out of the box that the messages would be published. They can be published in exactly the same commit order. So here is explanation about what is write-ahead log. It's append-only binary log for each row, and it's written before the data is it's written before the data files are written. So it helps Postgres with crash recovery out of the box, and the changes they group per transaction in commit order. And it exists in the shared buffer, and then it's flushed to the disk files. So maybe this image is more helpful to explain. This is the Postgres process architecture. So once you can connect to the Postgres, there is a postmaster process. It will create a child Postgres instance per connection. And then those child, they share multiple shared buffers. So like the data, they reside in the red one, the shared buffer, but you can see there is a wall buffer, which is write-ahead log buffer. So once you commit to the Postgres, then the changes, they first are written to the wall buffer. And then that wall buffer, they have to be synced to the wall files. And once that happens, then transaction is considered committed, even though in the shared data buffer, the data might not yet be synced to the data files. So that's kind of done for performance optimization in Postgres. And then the idea that we can get a separate connection and read the wall files of the Postgres to extract actually our outbox messages from those files. Then the data would avoid going through the shared buffer, and then it would avoid harming like our useful workloads on the Postgres. That's the idea of the log-based CDC. So I give you an example about these transactions. If we have a high load on the Postgres database, we have 3 transactions here. Just note that the green transaction would be rolled back, and the 2 red one and the blue one, they got committed eventually. But because it's kind of a high load, very concurrent, the execution is interleaved. So it can look like this, like execution of transactions in the Postgres system, but this is how it would end up in the write-ahead log file of Postgres. So what is remarkable here, the transaction which was rollbacked, it doesn't end up in the WoW file at all. And then transaction which committed first, in this case it's transaction 3, even though it started later than transaction 1, it will be on top of that. And then the numbers on the left side, they're offset. I'll explain a bit later. So now we can store outbox messages to Postgres to a separate outbox table, and we need a way how to read them efficiently if polling is not sufficient for our approach, if we have a high traffic. So there are multiple solutions. One of them is Debezium or Debezium server, which is written in Java, so it's not pure Go. And then the 2 solutions at the bottom, they're written pgogrepl. It's very low-level Go library, and there is PeerDB. It's a product which uses that low-level pglogrepl library. Let's start with Debezium. So it can come with 2 flavors, either connectors for Kafka Connect or standalone server, which can be run in Docker container. So you can configure that to connect to database, Postgres or MySQL, doesn't matter. And then it would read those outbox messages and send them to the configured sync like Kafka or something. So it's very mature product. It was started like a decade ago by Red Hat. It's open source and written in Java. So it's very mature, and this is the architecture. And the image below, it's architecture of a standalone server, which can be run in Docker container. So it has connectors for to read from the WoW file of Postgres or binlog of MySQL, and then it can publish the data. So to give you a flavor how it can look in config file, so you just run that in Docker container, you provide some config file. Example, you configure the source. In this case, it's Postgres. You need to provide database credentials. You need to configure publication name, replication slot name. I explain later about those. And then you say, okay, which table it should get the data from. And then in here, for simplicity, I configured HTTP sync, not Kafka, but just send data to HTTP endpoint. And then you can do single message transformation, which can configured below, because out of the box, it creates some envelope about Debezium, a lot of metadata. If you want to remove that one, you need to actually to unwrap that one, but it's very extensible. And out of the box, Debezium comes with Outbox Pattern solution, which is suitable for the Kafka Connect as Kafka Connect mode, Kafka connector. So then it actually guides you how to create the proper Outbox table, and then certain fields would be used to route to specific Kafka topic, and certain field would be used as a message key when published to Kafka. But if you don't use Kafka, then you can do similar things yourself with Debezium. And then I think this is quite common solution in multiple companies, as I heard. So they wrap Debezium with some Kubernetes CRD and operator, and operator would spawn a single pod deployment, and that pod has Debezium inside, and it would connect to the Outbox to the proper Postgres or MySQL, and then read the Outbox table and publish them to message broker to Kafka. All right. So, but the problem of Debezium, it's not pure Go. So, and this conference track is about Go. So let's explore more about what Go approaches are in the market, because potentially we can do it much more efficient in memory and probably speed. So this library, pglogrepl, it's a very useful library. It's the same offer as pgx driver offer. So very experienced person in Postgres and Go drivers. So it helps you to decode messages using logical replication protocol of Postgres. It includes basic example, but it's not in very active development, and it's very low level, but it can be used as a building block. So, but this library is very nice to introduce some concepts about Postgres logical replication, but it can be applied to different databases. So there is a concept of publication, replication slot, decoding plugin, and log sequence number. Let's start with publication. So publication is just a definition of the tables and operations which is going to be published to consumers. So it's not nothing active happens at the moment. We just define like, okay, what tables, like in the Outbox table, in Outbox Pattern case, it would be just an Outbox table probably, and then we would be published only in inserts. So so it's very configurable, and you can query the Postgres and see like what publications you have already configured. And this is the second code snippet, how it looks in Go using this pglogrepl library. You need to get the very low connection in that library, and then you can execute the query and you get the publication created in the Postgres, but nothing actually happens before you start because to start something interesting, I need to introduce the second concept, the replication slot. So replication slot is kind of a named position in the write-ahead log file, and it tracks like what's the progress of the consumer. So replication, it's a name because it has a name, like you have to provide a unique name. So the first select is a bit confusing because it actually creates the replication slot. But in the Go snippet it's actually create, it's not select. So you have to provide the name, and you need to provide a plugin. So the plugin in Postgres, there are multiple plugins how you can decode those messages out of the box. It's built in Postgres, and it's also very low level. So you need to do some additional work if you want to get actually useful data out of that. So WoW for JSON is useful to get JSON immediately. So you read from the Outbox table, and then you get like that in JSON immediately. But that would require to be installed as extension to the Postgres beforehand, and then it can produce JSON. So we need to configure the plugin PG. Let's use this low-level PG output plugin. So the most important part is here that we provide the publication name, and publication name is just definition of the tables which we want to be exported. And then we can start the replication. So that's actually the interesting things start happening. We need to provide the position in the WoW file where we start a replication, and then Postgres would start sending the messages from the table. So the one we configured in publication. So if there are actually changes happening in the Postgres in the table, then they start to be streamed to us. So we have to handle them in a message loop in a single Go routine. So we decode the messages. It can be of two flavors. It can be data or kind of keep alive health check. So and then if it's a message, if it's data message, then still there are multiple cases. It can be like actually our insert message, which we are interested because we inserted outbox message. It can be relation message, which is basically sent in the very first message, and it tells like what's the database structure, and then Postgres would send just only ID, so to save the bandwidth. And also we need send back like as a replication client, we need to send back to Postgres like what is our position, and position is not like a single position, it's multiple positions. So actually logical replication is hard. The conclusion is it's hard, but luckily we get some products which were built on this pglogrepl library, and one of them is PeerDB. Then I was exploring that library. I checked like who actually used that one, and I think that was the project with the most stars on the GitHub. It was a startup and acquired by ClickHouse, so it's written in Go, and some parts of that are in Rust. So it provides efficient data streaming, and basically it's in Go. So this is exactly what we need for this track. And this is how it looks. It comes with API and UI. I show you in UI, so we need to configure, we can configure like multiple peers. Peers is the common name for sink and source of the data. In here I configured Postgres and Kafka as the peers, and then we need to configure a mirror, and mirror is our actually replication flow that continuously sync data from, in our case, from Postgres to Kafka. And then I don't show the demo here, but this is what I prepared. So I went to Kafka UI, and then this is how the message looks like. So I was using Go Fake It library to generate some fake data, and then insert that and the orders and outbox messages to outbox table, and then I configured PeerDB to read that outbox table, and then to publish to Kafka, and then this is how it looks like in Kafka UI, and you can transform the messages using Lua scripts in PeerDB. So, but replication, logical replication, it comes with big pitfalls. Like once you, like the client stops sending proper offset, then Postgres would start keeping the files, WoW files. So ideally, it should archive some segments of the file, of the WoW files, and then delete them eventually, so it keeps it low disk space. But if clients start to misbehave, then it's quite common that Postgres eventually would fill up the disk space and crash because of that. So my takeaways that we should avoid microservices if they're not really needed, because that transactional Outbox patterns is because we migrated from like a single monolith Postgres to multiple services with sometimes not proper boundaries. So yeah, if you can do that in a single service, you don't need transactional outbox pattern. But if you really need that, then probably you can use like this queuing approach for low traffic. But for high traffic, you need something like Debezium and PeerDB, and Debezium can be wrapped in Kubernetes operator. And that's the end of my talk. Thank you for attention, and happy to answer your questions. I'm not sure I fully understand, but no, there is no transactional issue because we insert like the orders and outbox messages in the same transaction, but then we need to publish them, and there we introduce this kind of eventual consistency. So we don't publish immediately, but at some point of time it would be published. So I don't see here this transactional issue because we do that in the transaction. You can find me after the talk. We can discuss if you're still in doubt.
Okay. How would you handle horizontal scaling of the relay? Have you tried DB locking mechanisms like select for update?
So yeah, I mean, that's I mentioned it doesn't scale well because of the Postgres. So if you have like a higher traffic, then you should start using something like Debezium or PeerDB, but it comes with additional complexity and different kind of pitfalls, like bloat. So you have to be very careful when you start to use this logical replication approaches, and you have to monitor like what's your actually position, if it's advancing, what's your size of the wall, and so on. So you have to monitor that solutions. Yeah.
Thank you. Could we use pub/sub instead of a database to store the events?
Pub/sub. I'm not sure about how that's related exactly to transactional outbox pattern. There are some alternatives to that. In that article I mentioned, revisiting the outbox pattern, there are multiple alternatives, but they also comes with some side effects. So still, this transactional outbox pattern is kind of standard solution. So we still publish the message. So we can also discuss after the talk. I'm not sure I understand the questions fully.
Okay, so let's go with the next one. The outbox relay point may fail too, right? So then the state will be inconsistent. Can that happen?
Yeah, that's a good point. It can fail, but we have guarantee that it would eventually be published. So it's not like we are losing the message because the message is already in the database. So once outbox relay is up again, so eventually it would publish the message. So we don't lose the message. We just introduce delay, and potentially it can be a huge delay if it fails completely and it takes time to recover. But we don't. It's a different type of problem. But in the original problem, we had a risk of losing the message at all. Here we don't have this risk, but we publish it sooner or later.
Okay, thank you. How to handle big blobs in logical replication? Because I think that outbox relay funny face is just because of the relax point instead of relay point.
Yeah, for PeerDB, they have articles about blobs and about this toast. So I don't have personally big experiences that, but they have special articles about handling this toast and blobs. You can also discuss afterwards.
So we have 1 minute still left. So should the outbox pattern be in a separate Go routine?
So no, I mean so we have the writer, outbox writer, so it has to be in the same transaction. It shouldn't be in the same Go routine. It should be in the same transaction. And but then if it's the question about the outbox relay, then it doesn't matter. It can be a separate deployment unit. It might be a separate coroutine, but if it's a separate coroutine for Outbox relay, then potentially each pod has that, so they start to compete in each other because they actually need to get the messages and acknowledge them. So it's better to separate that as a kind of cron job or single pod, which has no contention with other. So, but if you really want, it can be a separate coroutine for the Outbox relay. If you have a single pod, I think, which is quite rare these days.
Do you think you can answer why not use something like temporal in a few seconds? No, just not seconds, but not so much time?
Yeah, temporal can be also used for Outbox Pattern, one of the options, and actually PeerDB use temporal under the hood. So yeah, potentially it can be used.
Good. Nikolay, thank you so much.
Thank you very
Final
much.
round of applause.
From ContainerDays Hamburg, this video is proudly presented by jackc.